Okay, this is a continuation of section 2.6 for MAC 1105. We've been looking at how to tell the domains of functions that have been combined. For instance, here you've combined the function x minus 6 with the square root of x minus 2 through the form of a fraction. And in looking to determine what the domain is, I was talking a lot about in examples A through G that the only things you really need to worry about is protecting fractions, not letting the denominator go to 0 because that'll make the entire fraction undefined, and also protecting even radicals, radicals with even indices. This happens to be one of those because this is a square root. The index is said to be a 2. So that means that it's an even radical. Those have to be protected. It just so happens that in this problem they have combined both of those issues. Not only do you have a fraction, but you also have a radical. So we really need to zero in on what's going on in the denominator, since that's the area that can't be 0. But then yet we also have to make sure that since this x minus 2 is underneath a square root, typically we would protect that situation like this. We would take the radicand and set it greater than or equal to 0. But since this particular radical also happens to be part of a denominator, we can't even let it be equal to 0. Because in letting it be equal to 0, we'd get a 0 down here, thereby making the fraction undefined. So we have to kind of tighten up the restriction here and not just go with the greater than or equal to 0, but make it just greater than 0. Throw away that equal sign if your even radical happens to be in the denominator. That's when you're going to do away with the equal sign. In solving this, we get x is greater than 2. Imagine if we had left that equal sign there. Then we would have x is greater than or equal to 2. And you can see what that would have done. If we would have allowed it to be greater than or equal to 2 by leaving that equal sign in, if it was 2, 2 minus 2 would be 0. Square root of 0 is 0. Whole fraction crashes. So that is why we got rid of the equal sign when the radical's in the denominator. Picture of this domain. This is what x is allowed to be. By solving this inequality, you're figuring out what x can be. This says that x can be 2 or greater. That is what it looks like on a number line. In interval form, the way we always state our domain, it would be 2, 2. That arrow means you're going off to any value in positive infinity. This next problem, I'm not going to do this one because it just mimics what was going on in part H, but I will jump to J, which has something new for us. Now we see pretty much what we're going to be doing once we get into this next section, where we're going to actually be combining two functions through either addition, subtraction, finding products, and also finding quotients. Here they have the sum of two fractions. And so since both of these have a denominator, we're going to have to protect both of the denominators. You see that this denominator has x plus 3. So the one value that would cause a 0 in this denominator and therefore is not allowed is the value x equal to 3, negative 3. We cannot use the value x equal to negative 3 because it would zero out that denominator and make this fraction undefined. Now, one fraction being undefined is just as bad as the other one being undefined, so this needs to be protected also. Because of the expression x is not allowed to be, it is best to put all of them onto one number line. You have to put all of them onto one number line because you're trying to combine the restrictions of this function together with the restrictions of this function. I mean, these appear as two different terms, all being part of one function, but when you start combining functions, it's going to just be considered one big function, and any restrictions for any one particular term need to be considered and all dumped onto the same number line. So x cannot be negative 3, and it cannot be 1. So you're going to see that, like several of the other examples we've had in this outlined thus far. You have a three-part area that the x values can lie in. They can be out here and they're good. So anything from negative infinity up to, but not including -3, that's all good. Anything from here to here is good, from -3 to 1. And anything from 1 to positive infinity is good. So there are several areas that are good, but you have to make yourself jump over the values that it cannot be. So we say that the domain is anything from negative infinity to -3, not including -3, or it can be anything from -3 to 1, or it can be anything from 1 to infinity. In interval notation, that is stated like this. Just as we've stated our other three-part domains, negative infinity, all the way up to, but not including -3, that parenthesis means that endpoint's not included, or is symbolized with the symbol, the union symbol. Makes us jump over the values that are not allowed. We can also have anything between -3 and 1, or we can have any x value between 1 and infinity. All of those are good, usable values, while -3 and 1 are not allowed. So that's the domain for that problem. Then we get into actually combining these ourselves, where we're given various functions. Here we have function f and g, and we're going to combine these functions through addition, subtraction, multiplication, and division. So in the first one, we have f plus, we're asked to combine 5x plus 3 plus x plus 7. This is the f of x function right here. This is the g of x function. So f plus g, there you have it there. Simplify it. 5x and 1x is 6x. 3 and 7 is 10. And then you're going to be asked, what is the domain for each combination? We've performed the combination of creating a sum. The domain is all real numbers, because the only domains that have restrictions in them, as you have seen throughout this worksheet, throughout this outline, are fractions or radicals. They have restrictions and values that are not allowed. Restrictions means values that are not allowed, but not a polynomial like this. This can be anything from -infinity to infinity. You're allowed to use any number on the entire number line. That's what it means, -infinity to infinity. When you go to do the difference, it's not going to change the domain, but you are going to get a different answer, of course. So this was the sum. Then here you're being asked to take f and subtract g. So here's f, subtract g. You might want to put the entire g function in parentheses just to remind you that you're going to be switching the signs here. Subtracting a polynomial means switch all the signs of the terms that come right after it. So -x and -7 will be combined with this 5x plus 3 to give us 4x. That would be 5x minus 1x, and then 3 take away 7 is -4. But this combination created through a difference is also a polynomial. It's not a fraction, and it's not a radical with an even index. So the domain is the same. There's nothing about it that needs to be protected as far as what people, what someone could come and plug in here. It could be anything from -infinity to infinity, and no number that you plug in will cause it to be undefined. So that states the domain. Next, we're going to be asked to do the product. So we're going to be multiplying 5x plus 3. That's what a product is, to multiply. And in this particular problem, since what we're multiplying are binomials, we're going to have to FOIL. FOILing is the process that allows us to multiply binomials. We have a binomial here. We have a binomial here. So FOILing, we go first times first, outer times outer, inner times inner. Each time we follow one of those arrows, we're multiplying. So 5x times x, 5x squared. When you multiply, you're adding the powers. 5x times 7, 35x. Following these upside down arrows, 3 times x, 3x, and 7 times 3, 21. Combining like terms, we end up with 5x squared plus 38x plus 21. And because this answer is another polynomial, just like we got in this part, not a fraction, not a radical with an even index, again, the domain, in other words, what you're allowed to plug in for x, can be anything from negative infinity to infinity. Moving on now to the quotient. We've also been asked to find the quotient, f divided by g. So f divided by g, that just means we put the f function on top, and the divisor is the g function. Now we finally get an answer that involves a situation where we need to protect it, or this could potentially become undefined. We have to stop that from happening by telling whoever's going to use this function what they're allowed to plug in and what they're not allowed to plug in. So to protect this denominator, we see that the only value that would create a 0 in the denominator is x equal to negative 7. So x is not allowed to be equal to negative 7. We're not concerned with the numerator because the only thing that has the ability to make the fraction undefined is the denominator. If you have problems stating the domain, the best thing for most students, they need to draw out what the domain values can be and can't be. So we start by drawing a number line and putting holes right where the numbers are that we're not allowed to use. When you put a hole there, it makes you jump over that particular value. It calls to your attention that particular value and the fact that you need to jump over it, or in other words, not use it. These are the things you can use, the shaded area. So anything from negative infinity to negative 7, or anything to the right of negative 7 can be used. So all of this from here to here is good, and then anything from here to here is good. And if you go and then state that in interval notation, all the number line does is assist you in being able to state the domain in interval notation. So always read it left to right. It can be anything from negative infinity up to but not including negative 7. Jump over this negative 7. So it can be anything from here to here, or it can be anything from negative 7 to positive infinity, or is represented by the union symbol. And then we state the other allowable values, 7 to infinity. And that is the domain for this quotient combination. This is the domain for the product combination. Okay, then we go into the next page, where again we are combining functions, but the functions are getting more complicated. They're starting to be second degree and so forth. That just makes certain parts of the algebra a little bit more difficult. So first let's do part A. Well, they're not actually numbered, part A, B, C, D's, but the first part is where we're doing f plus g. So in f plus g, we're going to be doing the f function, which in this case is 5x squared minus 4x plus 20. And we're going to be adding that to the g function. So all you can do, you can actually carry on with this because these are all polynomial terms, and you can just combine like terms. So we only have one squared term. We have a linear term here and a linear term here, both first degree terms. So negative 4 plus 1 is negative 3. So that combines your linear terms. Then as far as the 18, but the answer, this combination of a sum of the two polynomials, it's a polynomial itself. And for a polynomial, what you're allowed to plug in for x can be any number from negative infinity to infinity. It requires no protection because it's not a fraction and it's not a radical with an even index. Then when we go to do the difference, it's also going to come out to be a polynomial, and therefore we'll have the same domain. But the answer will come out different. So it's going to be the f function, 5x squared, minus 4x plus 20, minus the g function. Now when you minus that g function, it just causes both of these signs to switch, so that rather than x, positive x and negative 2, it'll be negative x and positive 2 that you'll be combining with the terms from the f function. So we already switched the sign down here. Let's combine like terms. We have one squared term. Then as far as the x's, we have a negative 4x from the f function and a negative 1x from the g function. When combined, that's negative 5x. So those are the x terms. And then for the constants, we have the 20 from the f function and the positive 2 from the g function. When combined, is 22. Again, we have a polynomial for the final answer, the combination through finding a difference. Domain for all polynomials that are not no radicals, no fractions, is negative infinity to infinity. Anything can be plugged in here. Okay, next we go and look at the product, where we're going to be multiplying two-term polynomial times a three-term polynomial. Now you can put whichever one you want in front, but you need to put both in parentheses. You're going to be doing an extended form of foiling. So instead of 4 products, you're going to have 6, and I suggest you put the shorter polynomial as the first polynomial, and then the longer one as the second one. That way when you go to draw your foiling arrows, they're not going to crisscross. They'll be nice and clear. Okay, so here's your when you're finding a product, doesn't matter whether you put the f function in front or the f function in back, if you get the same answer either way. This is just going to make it easier on you when you start to draw your arrows that show you what you need to multiply. You need to multiply 6 times. So the x gets multiplied by the 5x squared. It also gets multiplied by the negative 4x, and it also gets multiplied by the 20. That's 3 of the products you're going to find. The negative 2 in and of itself creates 3 products. It gets multiplied by the 5x squared, the negative 4x, and also the 20. Over here, we will begin to do those products. So now getting up here and following the short, the medium, long arrow. So x times 5x squared. Don't forget, when multiplying, you add up the powers on the like basis. So x times 5x squared, add up the square and the first degree term here, and you get 5x cubed. Doing the medium arrow, x times negative 4x, negative 4x squared. You're adding up the powers. X times 20, 20x. Now following the upside down arrows, negative 2 times 5x squared, negative 10x squared. Negative 2 times negative 4x for that medium arrow would be positive 8x. And then negative 2 times 20, negative 40. Combining like terms, you have only one cubed term. As far as squared terms, we have negative 4 and negative 10. When combined is negative 14. And then we have 20x and 8x. That's 28x. And then we also have a negative 40. Look at this answer. It's just another polynomial. It's not a fraction. It's not a radical with an even index. So your domain is anything from negative infinity to infinity. Okay, moving on to the quotient. In the quotient, you're going to put the f of x function on the top, which is the 5x squared minus 4x plus 20 over the g of x function. The g of x function becomes the denominator. Now, I would tell you to reduce before giving your answer. And the only way you can reduce is if this top factors But you have to be careful about that. I made a comment about this earlier in the section then, that when stating the domain, you have to do the domain before reducing. And if you are going to be able to reduce, the only way that's going to happen is if this factors. Now you can try factoring this by guess and check. You could also try splitting the middle term. Those were both methods discussed in Chapter 1 for factoring trinomials, especially when there's a leading term that's bigger than 1. That splitting the middle term is nice. And if this did factor, it's possible that maybe it would have a factor as part of the breakdown that canceled with this, and that would be the only way it would be reduced. But no matter what you try here, regardless of the method that you try, this doesn't factor. There's no numbers that would break that down into linear factors. So this is not going to reduce, and even if it did, you're supposed to do the domain before reducing. When reducing is possible, not possible in this case. It is not possible to reduce here, and that's just because the top left factor. But anyway, what is the domain? Only thing we need to protect is this denominator. It's the only thing capable of making this whole fraction undefined, and that's if it goes to 0. What would make it go to 0? If x is equal to 2. So x is not allowed to be equal to 2. If you want to draw that on a number line so that you get the domain correct, you can put a 2 with a hole and then show yourself all the x values that you are allowed to use. This is the only one you can't use, which is why there's a hole there. So you would say anything from negative infinity to 2, but not including 2, or anything on the right side of 2, as we have seen in many of these answers. You state that in interval notation like this, not including 2, that's why there's a parenthesis. Make yourself jump over the non-allowable value with a union symbol. So it can be anything from here to here, or anything from here to here. Okay, moving to this problem with the radical. You're not going to be able to do much here when you add, subtract, or multiply. There's just not much you can do, and that's because these are polynomial terms, and these are terms that are underneath a radical, underneath a square root symbol, and you can't combine those kind of numbers. So although you may be able to go as far as just showing what it looks like, there's the f function. And you're adding it to the g function, but that's as far as it goes as far as you showing it as a sum. You can't combine numbers under here with numbers that are on the outside of the radical. So it stops there, but you can do the domain. You have to look at each of these terms to see if any of them impose some kind of restriction. And you see that only the last term is one of those terms that has to be protected. So we protect any kind of radicand that's underneath a radical with an even index. We protect those unless they're in the denominator of a fraction, as has popped up in a couple of the examples. We protect them like this. We take the entire radicand and set it greater than or equal to 0. And then by solving that, you know what x can and cannot be. So to solve this, you would bring the 3 over here, resulting in x greater than or equal to 3. What does that look like on a number line? It would be 3 greater than or equal to. So you're allowed to use the number 3 or anything greater. So this is what x is allowed to be, set builder style. This is what it looks like on a graph, and this graph always helps us to get our interval notation correct. The domain is anything from 3 to infinity. Do f minus g, and you're going to run into the same roadblocks there. You have 1 function that's made out of is a polynomial, and then the thing you're subtracting is a radical. And so you have terms that are underneath the square root, which cannot be combined with these terms that are not underneath the square root. Again, regardless of whether there's a plus or a minus, that's not the thing that has anything to do with the domain. You're simply protecting this. So you'd be protecting the same term as you did here, and therefore the domain would come out the same for this problem as well as this problem. If you go to do the product, you're not going to be able to do much there either. You're going to be multiplying one function times the other. And the best you're going to be able to do is just put them in parentheses, indicating that you were about to do a product, but you really can't go any further with it. So it doesn't matter which function you put in front. I'm going to put the smaller function in front and say that we were planning on doing this. But there's really no point in going square root of x minus 3 times x squared, square root of x minus 3 times negative 12x, and writing it 3 times. You might as well leave it like this. My math lab will allow you to do that. Again, you have one portion of this product that needs to be protected. It's the same portion that you've had to protect in the sum and the difference combination. And so again, you're going to get the same domain. Domain here is, you find yourself protecting the same portion the same way for each of these parts, setting x minus 3 greater than or equal to 0, and therefore the domain keeps coming out the same. However, when you go to do the quotient, you're going to have the f function on top. Oops, I'm using the function from the problem before. You're going to have the f function on top, which is x squared minus 12x plus 35. And then you're going to have the g function on the bottom. And so because of that, you can't go any further with that quotient either. These are just not compatible functions where you could continue simplifying. However, you can protect it in order to answer the domain. Now this domain is sort of similar to this. I mean, typically we do protect the inside portion, the radicand of any kind of a radical that has an even index, like a square root. We typically do protect it by just taking and then or equal to 0. But this time, that little equal sign, letting it be equal to 0, that just won't do in this case. And that's because the radical's in the denominator. So we have to tighten up the restriction a little bit by saying, not that x minus 3 is greater than or equal to 0, but that it is simply just greater than 0. We can't let it be equal to 0 because this is in the bottom. Otherwise, we would do it like we always do. Okay, that's going to just give you pretty much the same thing, only the endpoint is not usable. If you add 3 and add 3, that's what this arrow means. You're adding 3 to both sides. You would get x is greater than 3. That looks like this. Instead of a bracket, it just has a parenthesis. Everything greater than or equal to 3 is allowable for this particular function. Written in interval notation, which is a big thing you're learning and getting good at in this section, is just do what the picture says. It's everything from 3. This means infinity. You're going out to positive infinity. Okay, on the last page of this section, we are looking at combinations. Instead of combining two functions through addition and subtraction, we are combining functions through substitution. So we have to get used to the kind of notation that we have here. Here, this is read when you're reading this symbolism here, f composed of g, where this is considered to be the inner function, this is the outer function, and we're going to end up plugging the inner function into that outer function. This means this is the inner function. It's just that it can be stated, instead of using this bubble right here, f composed of g, they can just use an extra pair of parentheses, and it's still read f composed of g. This is still the inner function, and you're always plugging the inner function into the outer function, which is what I'm going to demonstrate. Okay, so like in this first problem, they're giving you f of x is equal to x plus 3 and g of x is equal to 2x plus 7, and then they're asking you do f composed of g, g composed of f, then take those two answers one at a time and evaluate them at 2. So here's part A. Easiest way to remember this is that if you are going to plug g into f, there's no way to plug anything into another function, a function into another function, unless you open up the function that you're going to plug it into. You're about to plug in g into f. You need to open up that outer function. Here's what I mean. If you're going to open up the outer function called f, that means write that f function, but leave blank spots where the x's are, which is the comment that's being made right here. Okay, so the function f is x plus 3. So we're going to write x plus 3. Then we can take the g function and plug it into f by just plugging it into that open spot. So what is the g function? 2x plus 7. Okay, we can then combine like terms, which gives us, in this case, 2x plus 10. Okay, that is f composed of g in terms of x. Part B, we're going to go back the other way, and we're going to do g composed of f. That's what they've asked you to do in part B. G composed of f, and we're going to give our answer in terms of x. Again, always open up the outer function, not the inner function that's closest to x. Open up the outer function. You open it up by writing that function but leaving blank spots where the x's are. So this will be 2x plus 7. 2x plus 7, left a blank spot where the x is. Now go dump in that inner function, which is f of x. That's what you're plugging in here. When I did this one, I was plugging the g of x function in, and that's because it was the inner function. Okay, so that f of x function is just x plus 3. Now when you carry the distribution through, it's 2 times 7. So you get 2x plus 13 for that composition. Now you're being asked to use the compositions that you got in parts A and B and evaluate them at a certain value, and that would be 2. So you say take your f composed of g answer and evaluate it at 2. Our f composed of g answer is 2x plus 10, and if you're going to evaluate a function at a number, that means plug in the number for x. So here you get 2 times 2 is 4 plus 10, 14. So when you're evaluating at a specific value, you are plugging that number in. Next is taking the g of f function and also evaluating that at 2. So my g of f function was, the answer was 2x plus 13. I'm going to go 2x plus 13. I'm evaluating at 2. This gives you 4 plus 13, 17. Likewise, this last problem, you have a linear function, you also have a quadratic function. You're being asked to do the same operations. Do a composition of f and g, f composed of g, where g is the inner function. Then to go back the other way, doing a composition of g composed of f, where f is the inner function, and then using each one of these answers and evaluating them at a specific value too. Okay, so in part A, I'm going to do f composed of g. Okay, don't forget, open up the outer function and then you will plug the inner function into that open function. the f function, it is 3x minus 1. So 3x minus 1. Now go dump that g function right in there. Dump in that inner function. Happens to be 3 terms. 2x squared plus x plus 6. You're combining functions through composition. This 3 is a multiplier. It gets distributed to the 2x squared, the x, as well as the 6. That gives you 6x squared plus 3x plus 18 minus 1. Combining those two constants, you end up with 6x squared plus 3x plus 17. And that is f composed of g, or in other words, f with g plugged into it. In part B, you're going the other way. G composed of f in terms of x. This time we're going to open up the g function. This is going to cause you, in this particular part of the problem, to FOIL. And that's because you're going to be plugging in and squaring. You'll see what I mean when I do it. So we're opening up the g function, which is 2x squared plus x plus 6. 2x squared plus x plus 6. Remember, opening it up means to put a blank spot wherever you see an x. So the x that, now what we're plugging in here is this inner function. We're going to plug that right into the open spot. That f of x function is 3x minus 1. And you put it everywhere there's a blank spot. Now in this particular problem, this is what makes this harder than part A. You're squaring a binomial. There is a shortcut for that. Yes, you can write it as 3x minus 1 times 3x minus 1. Then draw all the foiling arrows, follow each of the 4 foiling arrows, and get the 4 products. I'm going to do it by a shortcut that I've introduced several times throughout chapter 1 and 2, and I'm going to keep doing it so you can, get good at it. But when you're squaring two terms like this, it's square, double, square. When you square the first time, you're squaring this first term, the number as well as the variable. So 9x squared. When you do the doubling part, you have to multiply this times this first. 3x times negative 1, negative 3x. But then you're doubling that coefficient. So it would be negative 6x. And when you square, you're squaring the back term, which would be positive 1. Don't forget, all that is being multiplied by 2. Okay, and then you also have the 3x minus 1 plus 6. So now we're going to try and combine like terms, but we have to distribute the 2 to everything here first. So we're looking at this as an 18x squared. 2 times negative 6 is negative 12x. 2 times 1 is 2 plus the 3x minus 1 plus 6. Now combining like terms, you see this is much more work than the part above it. So this would be, let's see, 18x squared. Then we would have negative 12x and 3x. That would be negative 9x. And then we would have, as far as our constants go, we have 3 constants. So 2 take away 1 is 1. 1 plus 6, 7. And there we have G composed of F. A little bit more rigid on the algebra side. Now we're doing parts C and D, where we take the answers we've created already, these polynomials, and we're evaluating them at the value 2. So this says take your f of g answer and evaluate it at 2. Our f of g answer was obtained in part A. It was 6x squared plus 3x plus 17. 6x squared plus 3x plus 17. And we are plugging in a 2. That's what it means to evaluate. You can put that right in your calculator and get the answer. Okay, so this is 6 times 2 squared plus a 6 in the middle plus a 17 at the end gives us 47. That's the answer for part C. D, we're taking our G of F answer and we're evaluating it too. So our G of F answer, here it is right here. A little bit of work involved there. It was 18x squared minus 9x plus 7. Okay, so G of F evaluated at 2 is 18x squared minus 9x plus 7. We're evaluating at 2 once again, and we can put that in our calculator. So that's going to be 18 times 2 squared minus an 18 right in the middle there, and then plus 7. And that turns out to be 61. That completes section 2.6.